All right, let's talk a little bit about pressure volume diagrams. So PV diagrams, as they're commonly called. And so basically, you're just making a graph. I don't know if you could hear that. That was my dog laying down in his crate. He's free to walk around the room. He just likes to lay in his crate sometimes. You make a graph of pressure versus volume. And so because it's physics, we like to use pascals or newtons per meter squared. And for volume, we like to use meters cubed. In chemistry, they like to use things like liters and kilopascals because they're weird. Okay, so we'd start at a point on these diagrams. You say, okay, given an initial pressure and an initial volume, so I'm just going to call it P1 and V1. It defines a point, right? But then you say, what if my gas expands at constant pressure? Up to some volume 2. Right? So it's gone from, let's say, point A to point B and expanded, right? So whenever you expand at constant pressure, that's called isobaric expansion. So isobaric means constant pressure. And then what if your gas then is going to contract? And it's going to contract. I'm sorry, I didn't do expand. Yeah, I did expand isobarically because it's constant pressure. Now it's not going to contract. The pressure is going to reduce. And it's going to reduce while your volume stays constant. And so it's going to follow that path. And now you're going to go to pressure 2. And so it's going to be an isochoric change. So isochoric means constant volume. So its pressure is reduced in isochoric process. So it's a constant volume. So I'll add a couple more terms to this in a little bit. But the word iso means same. So whenever you put iso on something, you're saying iso thing, that thing's not changing. Off the top of my head, I don't have a good trick to remember choric is volume, but like if you talk about in chemistry, you talk about like millimeters of mercury or bars or things like that. That's talking about pressure. So we're saying isobaric is constant pressure. So let's complete this process. Let's just say you then contract back isobaric contraction, and then another isochoric process to increase the pressure. And you make a cycle like this, and you can move around the cycle. So the question then will be, how much work did you do? So just since we're on the topic, another word that we might use sometimes is isothermal, which means, anyone guess? Bueller? Anyone? Constant temperature. And there's one other terminology which means constant something, because like if you look at PV equals nRT, and we're just assuming that all of these are for a closed system, so we're assuming that the number of moles doesn't change. So we're not. There's probably a term for that, but I don't know what it is offhand. But there's another term which is a little bit different since we've done the other three. I'll write down, and that's adiabatic, which is in terminology sounds a little different, but that means you're not doing any work. Or, I'm sorry, that does not mean that. It means no heat change. Wow. embarrass myself. But sometimes I forget things too, just like you guys. So I'm going to pause the video real quick and look up, make sure I'm right. Yeah, I'm correct on that. So it's no heat change. So a good way to remember that, for me at least, a little mnemonic device is Diab, like Diablo, like the devil. So about heat, so no heat exchange is you're not changing your heat in an adiabatic process. But we'll talk about the isotherms and adiabats later if we need to. All right. So how much work is done in this process? Well, if you guys are at all familiar with the idea that from integrals from calculus, you know that the change in work is equal to the pressure times the change in volume, right? So this is, I guess, I'm going to put minus on here because we were saying work done on the gas. Let's write that down for ourselves because it's important to remember. At least for me, because I'm used to working it the other way. Okay. So I want that minus sign here. So how much work is done on the gas during this process? Well, if you guys are familiar with calculus, you can look at this like dW equals minus PdV, right? Which probably tells you something. You can probably figure it out there. And for those of you who are not, this area is equal to the work done by the gas is this area, because we're going to have more work here. So whenever you have a single process, let's do another one of these. So I guess the way we've done this is going to give us negative work, by the way, up here. So I'm going to say work done by gas. That's what we've got here as the area. So let's look at another one of these. So I've drawn another process because you don't actually have to follow those 4 types. You can do anything you want with a gas as long as you can make it do it. But those 4 types are the special cases. So what if I have this case where I have it going from starting at A, going an isochoric process to decrease the pressure, then it expands isobarically, and then it's going to contract while changing the pressure to come here. How do I do that? Because before our formula said that we had to have constant pressure to use that formula, right? Because I don't have a delta pressure, it's a constant pressure. Well, I'm glad you asked. Thank you guys for asking. Remember how we said it's the area? So now, since we're going the other way, this is work done on gas. Is the area here. So it's very different. So the area of this triangle is what we are looking for. Because, so we can find the area of triangle, and that will get us the work done on gas. So let's put some formalism. If you are going counterclockwise in your process, see how this is going counterclockwise, then the area is work done on the gas, which is, we'll have a positive area. If you are going clockwise, you're getting work done by the gas, which has a negative value for us. So let's write this down. So area is negative and work is negative. Counterclockwise, area is positive. And work is positive. If we're defining work as work done on the gas. So if you were external energy being put into it, we're defining it that way. I think it might help if we broke this down a little bit. So if we have a pressure graph like this, pressure volume graph. So this process, when we go this way, this process, the gas is doing work, right? So all of this area, if you said how much work is done to do this, work, this is put out by gas. So this is energy leaving, so it's going to be a negative sign. Is all of this area. All right, but what if we had one where we said, the other process, what if we said you're going from here to here? How much work is done there? Well, no work is done because there's no area here. There's nothing under this line, right? I can't, even if I say, okay, like this little bit is under the line, it doesn't have any width, so no work. Okay, let's do another one. On the same process, if we're going back the other way, because we're doing that full square process, well, work done, the work is done on the gas here, right? Because you're contracting, so that means you are adding energy. This is going to have a positive value. So that's going to be a little bit tight, but we'll make it work. Oh, I'm missing some of my graph here, sorry. It says pressure, volume. And lastly, to complete my cycle, if I go from here to here, I have another isochoric process, no work is done, right? And let's label our graph. Okay, so in this one, energy leaves, right? So let's write this somewhere. Which tells me work is negative. In this one, energy is put in. All right, I hope that helps you guys. So to understand those four processes and what's happening. So if I want to know the net work done in the system, the total work done, well, it's going to be, this is the work leaving the gas, the energy leaving the gas, minus the energy being put in. So in a full cycle, it's this area minus this area. And when we do that, we just get the area of the square enclosed, right? We get that area. All right, I'll see you in the next one, guys.